An optical microscope usually does not help us to analyze the structure and behavior of battery materials. Therefore, we must find better tools for that, and one of them is a scanning electron microscope, where we can see much more details which cannot be seen with an optical microscope. Scanning electron microscopy, SEM, is a diagnostic tool to analyze surfaces to create a three-dimensional image. It uses electrons generated by a gun, and the beam of electrons will thus be focused via several lenses towards the surface of the sample. The electron beam then will interact with matter of the sample to generate secondary and backscattered electrons. In addition, it also creates other radiation, such as X-rays, may be developed. The incoming electron beam, the primary electrons, touches the sample and so interact with electrons and the nucleus of sample atoms. Direct interaction with electrons will result in secondary electrons that will be released from the sample. These then will be detected by the so-called secondary electron detector. This detector shows the surface of the sample due to the electrons' interaction with all other sample electrons, and these are everywhere in the sample. Another part of the beam that penetrates the sample up to about 2 micrometer will interact with the nucleus of the atoms and will be backscattered due to the charge of the nucleus. These electrons then are detected by the backscattered electron detector. This detector will monitor specifically heavy elements, as these interact with the electrons stronger than lighter elements. Besides these secondary and backscattered electrons, Auger electrons and X-rays may be emitted, and this kind of radiation is element specific. To understand how this happens, we must look at the energy levels of that specific atom. The incoming electrons may have enough energy to promote an electron from a lower energy level to a higher energy level. Once an electron has been removed, it is possible that other electrons in higher orbitals fall back in the created electron gap, under a radiation of X-rays. These X-rays thus can be measured with which is called EDS or EDX, Energy Dispersive X-ray Spectroscopy. It is important to realize that this radiation is element specific. This means that the recorded X-ray spectrum is a fingerprint of the element present in the sample. Even the intensities of the X-rays gives an indication of the concentration of the elements present in the sample. This typically happens in the subsurface area. Another elemental analytical technique that could be coupled to SEM is Auger electron spectroscopy. Here an electron falls back to a lower energy level, creating enough energy to release another electron from the outer orbital. This too is elemental specific and thus can be used to element analysis. But this typically happens only at the top surface of the sample. So let's see how certain electrode materials can be studied. Here we see a potential cathode material, lithium nickel manganese oxide. Two powders are viewed under the scanning electron microscope. One powder with and one without the coating of chromium oxide. The sizes of these nice crystalline particles are about 1 to 5 micrometer. The picture on the right hand side clearly shows a blurry coverage, indicating the coating. With EDS, elemental analysis can be done. The coating shows indeed to contain chromium. The coating itself is thin and allows the electrons to penetrate and touch the underlying material. This underlying material was lithium nickel manganese oxide, which can also be verified with this measurement. This lithium nickel manganese oxide has also been deposited as thin film on silicon wafers. These wafers are treated with an acid to create pyramid-like holes with specific depth. Here too we can observe nicely the coating, also the holes. Besides, we can see that the thicker layers may result in deviation of the layer thickness at the edges of the hole and in the hole itself. It is also possible to obtain various morphologies of lithium nickel manganese oxide by changing the deposition parameters, which is out of the scope of this MOOC. But it allows us to show the strengths of scanning electron microscopy to analyze surface morphology of matter. The various layers shown here range from smooth to very porous, say cauliflower-like structures deposited on silicon wafers. Silicon itself is known as an interesting electrode material at the negative electrode. Here too, silicon wafers are etched, but here merely to create a porous structure. This is necessary to cope with the expansion of silicon once lithium is being inserted. The etched silicon wafers are crushed to obtain these porous particles with specific sizes. In summary, scanning electron microscopy gives us information on morphology, and EDS coupled to SEM provides elemental analysis and their distribution.